And now I think it's time to actually go to the 3 talks that we have as accepted papers in the workshop. And without any further ado, because we're a bit late, I'm gonna give the mic to Johan from Lund University in Sweden. And he's gonna talk about performance modeling for speculative execution in cloud applications. So Johan, the floor is yours.
Yes, thank you. Can you hear me?
Yes, perfect.
Yeah, great. I just gonna share my screen real quick here. So can you see this screen and my pointer?
Yeah, all good.
Yes, good, nice. Then I will start. So my name is Johan Ruuskanen, and I'm a PhD student from the Department of Automatic Control at Lund University. And today I will be presenting some research that me and my co-authors have been doing on performance modeling for speculative executions for cloud applications. So this is actually a continuation of our work that we will be presenting at ICPE tomorrow. But in that case, we studied what's known as request cloning, and here we now have started to extend it to also cover speculative execution for certain scenarios. So the paper itself is a little bit mathematical maybe, but I will here try instead to focus on giving some intuition to what we have done and why we have done as we have. So if you're not familiar with the terms, cloning and speculative execution is in its basic essence a duplication of requests that are arriving to some kind of server system. And in cloning, you duplicate your request immediately, while in speculative execution, you instead duplicate after some set speculation time. So you have a request that are entering your server system, and you let that run for some time. And if that does not finish after your set speculation time, you duplicate that request and let that run. So the original request is then considered completed once your first duplicated request has finished. And that is also the answer which is returned to the client. All the other duplicated requests are simply disregarded. So then it's quite natural to ask yourself why you want to do this. I mean, by sending more requests to a system, you will increase the load. But basically, since server systems are a bit unpredictable, it's actually quite a good way to reduce the probability of getting unlucky assignments. For example, if you have many requests running and you are only dependent on one of them finishing, then you have quite low risk of all of those requests ending up in the tail of the response times, basically. So that makes it a good tool for making performance more predictable, and you can also use it to drive down tail latencies in systems. So in the aspect of modeling, speculative execution has mainly been done for straggler mitigation in big data frameworks, and this is also where most of the modeling has occurred. But we have taken a little bit of a different approach in this work by instead considering a generic queuing system under some certain assumptions. So the assumptions that we have made to make this performance modeling work is basically we consider that we have a system with M servers and independently and identically distributed service times under some rate mu. And the servers are also using this processor sharing discipline. So what this means is that your queues in your server, they don't really have any queuing, so to speak. Instead, all the requests that are in a server get an equal share of the available resources in order to compute. So for example, if you see this system here to the right, and in this server you have 3 requests, but all of them are simultaneously receiving 1/3 of the available resources at this time. We further also assume that we have some kind of request arriving with some rate lambda, and they are assigned over these M servers via the join shortest queue load balancer. And as you can see here, and speculative execution in this sense is then that once a request arrives and gets sent out here, then after as the set speculation time, that request is simply duplicated and returned to the load balancer and then placed again on the servers. And this then continues until one of the duplicates are completed. And under these assumptions, we can actually derive a performance model for speculative execution for this entire system. And also, if we assume that these arrivals are Poisson distributed, we can also obtain some accurate mean response time approximations for an entire system like this. So before I continue, I need to introduce a concept called synchronized service that we introduced in our IP paper. It's basically that that you have a server system with a couple of servers. And if you have requests that enters and are duplicated to all of the servers that are, and you also assume that the duplicates, they arrive and start being served at exactly the same time, and also are completed at exactly the same time. So as soon as any of these requests are completed, then that completion is returned and the rest of them are terminated. And that is happening at exactly the same time. And if we can guarantee this, we actually show that we can equivalently model this entire system as a single GD1 queue, where the service times are simply the minimum of the service times drawn from these queues. So, I mean, in reality, there is no such thing as a synchronous service. I mean, you will always have some delay here if you try to build a system like this. And also some delay cancellation. I mean, it's naive to think that we could actually have perfect synchronization, but what makes it nice that some types of system actually behave as they were synchronized, what is a concept that we are calling near synchronization, which we then can use this GD1 equivalent modeling for approximating behavior for. So we first show that this GSQ load balancer with PSQs, they actually act as they are near synchronized, which is quite nice. So if we have clones that are introduced in this type of system, then they will act as they are near synchronized. And this even applies to speculative execution. So for example, if you have a speculative clone that starts running in one of these systems, then it will receive the same processor share for the as the original request in the remainder of the processing time, which is nice because this we can actually use to derive a service time distribution model for our entire ESQPS system under speculative execution. And how we do that, I will show you with some plots here. So to the left here, we simply have the cumulative distribution function for our original request, and it's simply that request that is running at the moment. So it's nothing strange here. It's just some CDF. But at this speculation time S1, this speculation clone is sent out to the system. And then suddenly we instead have two requests running at the same time with two different cumulative distribution functions. But since our system is acting as it is near synchronized, we can actually form the joint probability distribution of the first one that finishes of these two. And we can use this to spline it together with this first service time CDF to create this new service time CDF for the entire speculative execution system, given that we send a speculative clone at S1. And this can then also be iterated. So we can actually add more and more speculative execution times to this system. So we just iterate this B part and then the C part again to create a new entry for S2. So in a more general term, we can introduce some kind of ordered set, which we call SN, which is basically a set of all these speculation times that we want to use. And this can be used then to create this entire service time CDF for the entire speculation speculative execution system, basically, which is nice. But speculative clones does not only reduce the service time of the system. I mean, we are adding extra packets to our server system, so we are also increasing the load. And to model this, we first introduce what's known as the server, what we call as the service fraction, and it's basically the new service rate divided by the old service rate. And we also introduced this arrival factor, which is how many more packets are actually running in the system at a given in stationary mean. And you have like for the one here is for the original request, and then we have the sum over all these SNs. And our FP here is the probability that the speculation clone I is actually sent to the system. And this other fs is the time that the speculative clone I spends in the system compared to the original request. So by using this, we can actually derive how much more packets are actually running in the system compared to not having any speculative clones at all. So we can then use this to form this load factor by dividing these two factors. And then this actually models the load change of the system. For example, if this is smaller than 1, then that would indicate that we would have a reduction in load using our speculation scenario SM. And further, we can use this to also model the utilization of the system. And if our model then is accurate, then this could be used for determining, for example, if a system is stable or not, which could be a nice thing to have. So one thing to note here is that this arrival factor does not imply that we have a change of arrival rate of the original request. Instead, to model the effect on our original request, we do this with a decrease in available resources. For in our case, it's the amount of servers which we decrease. So we form this expression here, which is simply the amount of servers divided by this arrival factor. And one a little bit funny and strange thing to notice here is that this m will actually be a real number and not an integer. This might seem strange that we in our model can have 3.67 servers, for example, but you can think of it as a mathematical abstraction. Okay, so this is actually quite nice because we by doing this introduction instead and keeping the arrival rate as it is, we do not change the properties of the arrival rate distribution. And if we then assume that we have Poisson arrival to our system, then we will still keep our arrivals Poisson distributed in our model, which then makes it we can use this GSQPS formula for mean response time from this paper by Gupta et al., which is quite accurate to get this expression here. It's basically a bunch of functions and some parameters that we now have access to. Okay, so this actually gives us a way of modeling both the utilization and mean response times for these GSQPS systems under speculative execution. But the question still remains on how good this model actually is. I mean, for all we know, it can be terrible. But to shed some light on this, we performed some experimental evaluations using the cloning simulator from our ICFE paper, but extended to also support speculative execution. So in our experimental evaluations, we assumed that we had Poisson arrivals, and we also assumed that our service times were Pareto distributed, and we had 10 servers. Then we ran experiments many times over a quite long time with different utilizations and some different speculation scenarios here. And then from the experimental data that we get out, we can estimate the utilization and mean response times, and then compare them to the ones that our model will actually predict. So in our first graph here, we have the utilization on the x-axis, and then on the y-axis we have the simulated utilization for a specific speculation scenario divided by the utilization predicted by our model. As you can see, they are actually quite similar all the time, which is nice. We see we get a little bit worse with increasing utilization and also with decreasing number of speculation clones. But I mean, it's still within 1% for this particular case, which looks nice. And we also want to compare what will happen with the mean response time. So here we have the mean response time of the simulation under a specific speculation scenario divided by the mean response time that our model will predict. And we also see here that, as we did before, that for increasing utilization, our approximation gets worse. And also for increasing the speculation clone count, we also get a bit worse performance. The performance decrease in when increasing utilization can be mostly attributed to the fact that this near synchronicity of the GSQPS system becomes worse the higher utilization we have. So basically our approximation of this near synchronicity, it's a hard word. It becomes less and less the higher utilization we have, basically. So We also wanted to compare how specific speculation execution scenario actually changed the mean response time compared to using no speculative execution at all. So this done, we did this, and this is the plot. So we have the utilization on the x-axis, and on the y-axis we have the mean response time of a certain speculation scenario, the simulated one, divided by the simulated mean response time using no speculation at all. So it's simply just the novel GSPPS system. And here we can see at a low utilization, we are actually always better in the mean response time of using speculative execution. But as we increase utilization, we first pass this one line here first for S3 and then for S2, where suddenly it becomes worse to use speculative execution than to simply use the normal system. But a little bit surprisingly maybe is that this case where we only had this single speculative clone S1, we actually get a better and better performance the more the utilization is increased, or better relative performance of not using speculative execution at all, which seems quite nice. Yeah, and with this small remark, I will leave you with a conclusion. So for a GSPPS system, we have given a novel performance model for speculative execution, assuming service with IID service times, and also if our Poisson or our arrivals are Poisson distributed, then we can also derive an approximation for the mean response time. And at least according to our experimental evaluation, our model at least seems somewhat accurate and usable. So in the future, natural extension to this is, for example, to consider how to best choose this speculation scenario. For example, if we have a given utilization, a given system, how could we optimize over this variable so that we get the optimal mean response time or optimal 95th percentile or something like that. Yes, that was all for me. Thank you for listening. If you have any questions, you can ask them now, or you can send me or Tommi email at these addresses. Thank you.